What if I told you that right now, at this exact moment, the universe is tearing itself apart faster than the laws of physics say it should be, and every measurement we take makes the problem worse, not better? Not a small discrepancy, not a rounding error, not something that can be explained by better telescopes or more precise calculations. The universe is expanding 9% faster than our best theories predict. That's like driving from New York to Los Angeles and arriving in San Diego instead. The math doesn't work. The physics breaks down. And nobody, not Einstein, not Hawking, not any living physicist, can explain why. November 2025. The James Webb Space Telescope released its most precise measurements yet of the universe's expansion rate, the Hubble constant, how fast space itself is stretching, galaxies flying apart, the cosmic fabric inflating, and the number came back at 73.2 kilometers per second per megaparsec, with error bars tighter than ever before, certainty higher than ever before, problem more undeniable than ever before. But there's another way to measure expansion, using the cosmic microwave background, the afterglow of the Big Bang, radiation from 380,000 years after the universe began, pristine physics, early universe conditions, different method, independent calculation, and that measurement gives 67.4 kilometers per second per megaparsec. The difference is 5.8 km/s MPC. That's 9% faster. And the error bars don't overlap. These aren't consistent measurements with slight variations. These are contradictory results, both extremely precise, both extremely confident, both claiming to be correct. Both can't be right. This is called the Hubble tension, and it's been getting worse for a decade. Every new measurement from Webb confirms it. Every refinement of cosmic microwave background data confirms it. The tension isn't resolving. It's intensifying. Like the universe is screaming at us that our understanding of physics is incomplete, fundamentally broken, missing something crucial. Either our measurements are wrong. Every telescope, every method, every observation for 15 years is systematically flawed in ways we can't detect. Or our theories are wrong. General relativity, dark energy, the cosmological model that's worked for a century needs to be rewritten. Or something new exists, new physics, new forces, new particles we've never imagined affecting the universe's expansion in ways we've never predicted. And here's what makes this terrifying. If the universe is expanding faster than it should, if dark energy is stronger than our models predict, if the acceleration is increasing beyond what we calculated, then the fate of the cosmos is different than we thought. The heat death, the big rip, the end of everything. It's all on a different timeline. And we don't know which one. Some models suggest the accelerating expansion will tear apart galaxy clusters in 100 billion years. Others suggest it accelerates faster, tearing apart galaxies in 50 billion years. Some extreme models suggest acceleration continues increasing, eventually tearing apart stars, then planets, then atoms themselves. The universe doesn't just expand and cool. It rips itself to pieces. And we don't know if that's 100 billion years away or 10 billion years away, because we don't understand why it's expanding so fast in the first place. If you want to fall asleep exploring the biggest crisis in cosmology, understanding why two perfect measurements give impossible results, learning what dark energy might actually be, discovering what happens if the expansion keeps accelerating, and realizing that everything we thought we knew about the universe's fate might be wrong, subscribe right now. Every week we explore cosmic mysteries that challenge the foundations of physics. This is the Hubble tension, the crisis that's breaking cosmology, the problem that gets worse the more we study it. Let's investigate why the universe won't behave the way it should. 1998, Mount Hopkins Observatory, Arizona. Dr. Adam Rees was analyzing data from distant supernovae, type Ei supernovae specifically, the gold standard of cosmic distance measurements. Standard candles, astronomers call them, exploding stars that all reach the same peak brightness. Compare apparent brightness to known actual brightness. Calculate distance. Simple, reliable, precise. Reese was measuring supernovae in distant galaxies billions of light-years away. Looking back in time, seeing the universe as it was billions of years ago. The project's goal: measure how fast the universe was expanding in the past. Compare to present expansion rate. Determine if expansion was slowing down as expected. Everyone expected slowing. Gravity pulls everything together. The Big Bang threw everything apart. Over time, gravity should slow the expansion. Like throwing a ball upward. Gravity slows it, eventually stops it, maybe even reverses it. That was the expectation. The universe expanding, but decelerating, gradually slowing, eventually stopping, maybe contracting. The big crunch, but the data showed something impossible. The distant supernovae were dimmer than expected. Not by much, about 25% dimmer. That meant they were farther away than predicted, farther than they should be if the universe was slowing down. The only explanation: the universe wasn't slowing down. It was speeding up, accelerating, expansion getting faster over time. "This can't be right," Reese told his colleague, Dr. Brian Schmidt. "We've made a mistake. The data's wrong. We need to check everything." They checked everything: calibration, dust extinction, selection biases, systematic errors. Spent months verifying, reobserving, recalculating. The result didn't change. The universe was accelerating, expanding faster now than billions of years ago. Something was pushing space apart, overwhelming gravity, driving cosmic expansion. They published in 1998, simultaneously with another team led by Dr. Saul Perlmutter. Both groups found the same result: accelerating expansion. The discovery that would win them the 2011 Nobel Prize in Physics and create the biggest mystery in modern cosmology. The discovery required new physics, something causing acceleration, something filling space, pushing outward. They called it dark energy, not because it was dark, because nobody knew what it was. Unknown, mysterious, accounting for 68% of the universe's total energy density, the dominant component of reality, and completely unexplained by physics. But at least the measurements agreed. Both supernova teams got consistent results. The acceleration was real. Dark energy existed. The universe's fate was sealed. Not a big crunch. An eternal expansion. Accelerating forever. Galaxies flying apart. Universe growing cold. Heat death trillions of years in the future. Except there was a problem. A measurement problem. To calculate acceleration, you need the expansion rate, the Hubble constant, how fast the universe is expanding right now. And different methods were giving different answers. Dr. Wendy Friedman led the Hubble Space Telescope Key Project, 1990s and 2000s, measuring the Hubble constant using Cepheid variable stars, stars that pulse with regular periods. Period relates to luminosity. Bright stars pulse slowly. Dim stars pulse quickly. Measure the period. Know the luminosity. Compare to observed brightness. Calculate distance. Use distance to calibrate other measurements. Build up cosmic distance ladder. Measure expansion rate. Friedman's result: 72 km/s MPC, with error bars of about +d8. Pretty good precision for the time. Generally accepted. Used in cosmological models, seemed consistent with everything else. But then came Planck, European Space Agency's Planck satellite, launched 2009, measuring the cosmic microwave background with unprecedented precision. The CMB is the oldest light in the universe, radiation from 380,000 years after the Big Bang. Before stars, before galaxies, just hot plasma cooling. Photons finally able to travel freely. That light has been traveling through space ever since, stretched by cosmic expansion. Now visible as microwave radiation, filling the sky uniformly. The CMB contains information about the early universe, its density, its composition, how fast it was expanding. Tiny temperature fluctuations encode physics. Measure them precisely enough, and you can extract cosmological parameters, including the Hubble constant. Planck measured the CMB for 4 years, 2009, 2013. Data released 2013, 2018. The precision was extraordinary, the best measurement of the early universe ever obtained. And from that data, cosmologists calculated the Hubble constant, using the standard cosmological model, Lambda-CDM, the model that had worked for decades, the model that explained everything from galaxy formation to cosmic structure. The result, 67.4 km cm/PC, with error bars of +20.25, incredibly precise, 10 times more precise than previous measurements. Definitive, solid, unquestionable. Except it contradicted Friedman's measurement. 72 versus 67.4. That's 7% difference, outside the error bars of both measurements. They couldn't both be right. Something was wrong. Either the local measurements were systematically flawed, or the CMB calculation was wrong, or the cosmological model was wrong, or something completely new was going on. Initially, most cosmologists assumed it was measurement error. 7% isn't huge. Systematic errors could explain it. Better observations would resolve it. The tension would disappear with more data. Just a matter of time. Except it didn't disappear. It got worse. 2011-2025. Over 14 years, cosmologists refined their measurements, improved telescopes, better calibrations, more supernovae, more Cepheids, more precise distance measurements. Every improvement was supposed to bring the two values closer together, resolve the tension, restore consistency. Instead, the gap widened. The confidence in both measurements increased, and the contradiction became undeniable. Dr. Adam Riess continued leading supernova observations, using Hubble Space Telescope, measuring Cepheids in nearby galaxies, calibrating Type Ia supernovae, building the cosmic distance ladder step by step. Each step verified independently. Each measurement cross-checked multiple ways. 2016, Riess reported 73.2 kilojoules SMPC plus 1.7. Better precision, higher value. Farther from Planck, 2019, 74.0 plus 1.4. Even higher, even more precise, even more contradictory. 73.5 plus 1.4. Slight decrease, but still way above Planck. 2022, 73.0 plus 1.0. Error bars shrinking, confidence increasing. Value stable around 73 point. Meanwhile, CMB measurements improved too. Planck's final data release. South Pole Telescope observations. Atacama Cosmology Telescope. All measuring CMB with exquisite precision. All calculating Hubble constant from early universe physics. All getting values around 67 to 68 kiliri ses MPC. The contradiction was solid, locked in, undeniable. 73 versus 67, 9% difference. 6 sigma discrepancy. That's astronomically significant. 6 sigma means 1 in 2 million chance of random error. This wasn't statistical fluctuation. This was real disagreement, real tension, real crisis. Dr. Wendy Friedman started the Chicago Carnegie Hubble program. Different approach, using red giant stars instead of Cepheids. Red giants have a consistent peak brightness. Tip of the red giant branch, TRGB. Another standard candle. Independent of Cepheids. Different systematics. Different potential errors. If Cepheids were wrong, TRGB would show it. If both methods agreed, confidence in local measurements increased. Results published 2019-2021. TRGB gave 69.8 kD, Kiers MPC plus 1.9 between Riess and Planck, not resolving the tension, adding confusion, 3 different values. Which was right, but further refinement favored the higher value. 2024 TRGB results, 72.6 plus 1.4, back toward Rias, confirming local measurements around 72 to 73. Problem wasn't sea feeds. Problem was real tension. Real discrepancy. Then came James Webb Space Telescope. Launched December 2021. Operational July 2022. Infrared capability superior to Hubble. Seeing farther. Seeing clearer. Measuring Cepheids better. Reducing uncertainties. Resolving systematic errors that might have plagued Hubble. If the tension was from measurement error, Webb would fix it. The higher precision would show Rees was wrong, or show Planck was wrong, or show they were actually consistent when measured carefully enough. Dr. Rees's team got early Webb time, observed Cepheids in multiple galaxies, cross-checked against Hubble, verified calibrations, calculated distances, derived Hubble constant. November 2025 result, 73.2 kilo, coincidence MPC plus 0.8, same value as Hubble measurements, but more precise. Error bars tighter, confidence higher. Webb confirmed Rees. The local universe was expanding at 73, not 67. The tension was real. This eliminates measurement error as an explanation. Rias announced at the American Astronomical Society meeting, Webb and Hubble agree, multiple methods agree. Local measurements consistently give 73. CMB consistently gives 67. Both are right. Both are precise. Both are contradictory. Something fundamental is wrong with our understanding. The crisis was official. Not disputed anymore. Not debated. Accepted. The universe was expanding 9% faster than physics predicted. And nobody knew why. Dark energy. The term cosmologists use for whatever causes accelerating expansion. But dark energy isn't an explanation. It's a confession of ignorance. A placeholder. A name for the 68% of the universe we don't understand. Einstein introduced it first. 19 to 17. The cosmological constant, lambda. A term in general relativity representing energy density of empty space. Einstein added it to make his equations produce a static universe. Gravity pulling inward. Cosmological constant pushing outward. Balanced. Unchanging. The universe Einstein wanted. Then Hubble discovered expansion. 1929. The universe wasn't static. It was growing. Einstein removed the cosmological constant. Called it his biggest blunder. Except it wasn't. Because in 1998, when Rees and Perlmutter discovered accelerating expansion, the cosmological constant came back. Lambda wasn't zero. It was positive, small, but non-zero, causing acceleration. The cosmological constant interpretation of dark energy is simple. Space has energy, empty space. Vacuum energy. Quantum field theory predicts this. Virtual particles popping in and out of existence. Zero-point energy of quantum fields. Space isn't empty. It's seething with quantum activity. That activity has energy density. That energy density creates gravitational repulsion. Causes expansion, except the calculated vacuum energy is wrong. Spectacularly wrong. Quantum field theory predicts vacuum energy density about 10 or 120 times larger than observed. That's 1 followed by 120 zeros. The worst prediction in physics. Off by more than the number of atoms in the observable universe. If quantum vacuum energy were that large, the universe would have exploded instantly, inflated to infinite size in a fraction of a second. Nothing would exist, so there's a cancellation. The quantum contributions somehow cancel to leave a tiny residual. The observed dark energy. But canceling to 120 decimal places requires fine-tuning so extreme it's essentially impossible. Like balancing a pencil on its point, but 120 orders of magnitude more precise. Nobody knows how this happens. Nobody knows why the cancellation is so perfect. Nobody knows what mechanism produces it. The cosmological constant problem is the biggest unsolved problem in physics, Dr. Steven Weinberg said before his death. We observe dark energy. We can measure it, but we can't explain it. Can't calculate it from first principles. Can't understand why it has the value it does. It's a number we measure and plug into equations, not a number we derive from theory. That's not how physics is supposed to work. Alternative explanations exist. Maybe dark energy isn't constant. Maybe it changes over time, evolves, becomes stronger or weaker. This is called quintessence, a dynamic field, like the Higgs field but affecting expansion instead of mass. Quintessence models predict different expansion histories, different values of the Hubble constant at different times. Maybe the early universe expanded at one rate, the current universe at another. That could explain the Hubble tension. CMB measures early expansion. Local measurements measure current expansion. If dark energy evolved, they'd be different. Dr. Paul Steinhardt at Princeton proposed quintessence in 1998. Dark energy might not be constant, might be dynamic, a field that rolls slowly, changes gradually, over billions of years. That changes cosmological predictions, changes what we'd measure from the CMB versus local observations. But quintessence has problems too. Fine-tuning problems, coincidence problems. Why is quintessence becoming important now? Why not earlier? Why not later? The timing seems suspicious. Anthropic principle arguments get invoked. We observe this epoch because earlier epochs couldn't support complex structures. Later epochs won't support them. But that's philosophy, not physics. Unsatisfying. Other models get more exotic. Modified gravity. Maybe general relativity breaks down at cosmic scales. Maybe the inverse square law of gravity changes. Maybe additional forces exist at extremely large distances, modifying expansion, changing dynamics. André D.D. Modified Newtonian dynamics was originally proposed to explain galaxy rotation without dark matter. But cosmological versions exist. TVES, tensor vector scalar gravity. Other theories modifying Einstein's equations, adding terms, changing predictions. These models can explain acceleration without dark energy. Gravity itself creates apparent expansion, but they struggle with other observations. CMB, large-scale structure, galaxy formation. Getting one thing right makes other things wrong. No modified gravity theory explains everything standard cosmology explains, plus the Hubble tension. At least not yet. While theorists debated dark energy, observers kept measuring, getting better data, tighter constraints, clearer pictures. Every year, measurements improved, and every year, the tension persisted. Got worse, became more undeniable. Dr. Dan Skolnick at Duke University led the Pantheon Plus Supernova Survey, published 2022. Largest collection of Type Ia supernovae ever assembled. In 7 supernovae, spanning redshifts from 0.001 to 2.26, covering 75% of the universe's history, most distant reaching back 11 billion years. When the universe was just 3 billion years old, each supernova carefully analyzed, light curves measured, peak brightness determined, distances calculated, expansion history reconstructed, the most precise supernova cosmology dataset ever created. Result: 73.4 Kier, Computes, MPC, plus 1.3. Consistent with Reese. Confirming local measurements. Contradicting Planck. The tension was in the supernova data broadly, not just Reese's sample, not just Hubble observations. Every large supernova survey found high Hubble constant values. Dr. Sherry Suyu at the Max Planck Institute used a completely different method. Gravitational lensing time delays. When a massive galaxy sits between us and a distant quasar, gravity bends light, creates multiple images of the same quasar. Each image takes a different path, different travel times. The quasar varies in brightness. Measuring the time delay between images, seeing the same variation, gives the distance. No standard candles needed. Pure geometry and general relativity. The H0-LeCo collaboration, H0 lenses in Cosmo-Grail's wellspring, measured 6 gravitationally lensed quasars, 2016-2020. each giving independent Hubble constant measurement. Combined result, 73.3 km/h SMPC plus 1.8, another confirmation. Another method, another data set. Same answer, 73, not 67. The local expansion rate was fast, consistently, across multiple measurements. Multiple techniques, multiple teams. Meanwhile, CMB measurements also improved. The Atacama Cosmology Telescope in Chile, the South Pole Telescope, both measuring CMB polarization. Smaller angular scales, better systematics, confirming Planck, refining parameters, getting 67.3 to 67.9, always around 67, never reaching 73. Dr. Colin Hill at Columbia analyzed CMB data differently, searching for systematic errors, foreground contamination, instrumental effects, anything that could bias the result toward 67 when the true value was 73. He found nothing. The CMB measurements were solid, robust, trustworthy. The CMB gives 67, Hill concluded. That's not changing. The systematics are controlled. The physics is well understood. If the true Hubble constant is 73, the CMB should show it. But it doesn't. That means either our cosmological model is wrong, or there's new physics between the CMB epoch and now, something that changed the expansion rate, something we didn't include in our model. Dr. Licia Verde at Barcelona developed statistical frameworks, comparing all measurements, weighting by precision, accounting for systematics, checking for hidden biases. Could the measurements be reconciled? Was there a value that explained everything? Answer: no. The measurements weren't reconcilable. 67 and 73 were incompatible given the error bars. Statistical analysis confirmed what everyone saw. This was real tension, real disagreement, real crisis. Verde published the definitive analysis in 2023. The Hubble tension is not a statistical fluctuation. It's not measurement error. It's not a problem with one specific data set. It's a systematic discrepancy across multiple independent measurements. The early universe data gives 67. The late universe data gives 73. Both are right. Both are precise. And physics can't explain the difference. If measurements aren't wrong, and standard cosmology can't explain both, then new physics must exist. Something changing the universe's expansion between the CMB epoch and now. Something affecting measurements. Something we haven't discovered. The possibilities are vast and weird. Each proposal trying to bridge the 9% gap. Each creating new problems while solving the Hubble tension. Early dark energy, proposed by Dr. Vivian Poulin at Johns Hopkins. Idea: dark energy wasn't constant. In the early universe, before recombination, dark energy was stronger, caused faster expansion, made the sound horizon smaller, changed CMB predictions. When you fit the CMB with this model, you get a higher Hubble constant, around 71, closer to local measurements. The physics: a scalar field that was dynamically important early on, then decayed, became negligible. Now it's rising again, creating current acceleration. But its early presence changed the expansion history, changed how we interpret CMB, changed the derived Hubble constant. Problem: fine-tuning. Why did the field decay precisely when it did? Why is it rising again now? The timing seems orchestrated, unnatural. Also, early dark energy affects other cosmological observables, makes predictions for large-scale structure. Galaxy formation: so far, observations weakly disfavor it. But not definitively. Still viable. Still under investigation, extra-relativistic species. Maybe the early universe had more particles than we thought. More types of neutrinos, or other relativistic particles we haven't discovered. These contribute to radiation density, change expansion rate during the radiation-dominated era, affect CMB predictions. Adding energy density in radiation increases the inferred Hubble constant from CMB. Gets you from 67 to 69. Not enough to fully solve the tension, but helps, reduces the gap. Problem: particle physics. We've measured neutrino species precisely. There are 3. Adding a 4th requires it to be sterile, not interacting normally, allowed but unmotivated. No particle theory predicts it. Also, extra radiation affects Big Bang nucleosynthesis, changes abundance of light elements, helium, deuterium, lithium. Observations constrain this. Extra radiation is marginal, barely allowed. Not obviously correct. Decaying dark matter, proposed by several groups. Maybe dark matter isn't completely stable. Maybe it decays slowly, very slowly. Lifetime longer than the age of the universe, but not infinite. As it decays, it releases energy. That energy goes into radiation, or into dark energy, changing the expansion history. If dark matter decayed more in the past, it changed the early universe expansion, changed CMB predictions, changed the derived Hubble constant. Properly tuned, this bridges the gap, gets CMB measurements to agree with local measurements. Problem: why does dark matter decay? What does it decay into? How do we detect the decay products? Nobody knows. Dark matter is already mysterious. Decaying dark matter is even more mysterious. Adds complexity without clear motivation. Possible, not proven, not even well evidenced. Modified gravity, Part 2. Maybe Einstein was wrong. Not completely, just slightly. General relativity works perfectly at solar system scales, measured to extreme precision. But maybe at cosmic scales, billion light-year distances, the equations change. Additional terms matter. Modify expansion. Dr. John Moffat proposed scalar tensor vector gravity. Adds new fields. Changes cosmological predictions. Can explain Hubble tension. Can explain galaxy rotation curves without dark matter. Can explain some structure formation without dark energy. Ambitious theory. Explains much. Also complicated. Many parameters. Hard to test definitively. Problem: every modified gravity theory that explains the Hubble tension struggles with something else. CMB temperature power spectrum. Matter power spectrum. Supernovae Ia cosmology. Getting everything right simultaneously is hard. Standard cosmology succeeds because it's simple. Lambda-CDM has just 6 parameters. Explains everything from nucleosynthesis to current expansion. Modifying it risks breaking what works while fixing what doesn't. Interacting dark energy, dark matter. Maybe dark energy and dark matter aren't separate. Maybe they interact. Exchange energy. Dark energy gives energy to dark matter, or vice versa. Changes the expansion history, changes clustering, changes observables. Dr. Weiqiang Yang proposed models where dark energy couples to dark matter. The coupling modifies expansion, can raise the Hubble constant inferred from CMB, can explain the tension, also predicts specific effects on galaxy clustering, structure formation. Large-scale structure surveys can test it. Problem: why do dark energy and dark matter interact? What's the coupling mechanism? How strong is it? And why this specific strength? Tunable parameters, ad hoc additions. Not obviously right, just possible. The common theme: every proposal adds complexity, adds parameters, adds unknowns, and most don't fully solve the tension. They reduce it, narrow the gap, but don't eliminate it. Moving from 67 to 70 isn't enough when measurements show 73. You need to get all the way there, or explain why measurements are systematically biased. As of November 2025, no new physics proposal is widely accepted. No theory has solved the Hubble tension convincingly. The crisis continues, the gap remains, and cosmology is stuck, unable to move forward without understanding why the universe expands at contradictory rates depending on how you measure it. If the expansion rate is higher than we thought, the universe's fate changes. The timeline changes. The end changes. Everything we predicted about the far future needs recalculating. Standard cosmology predicts heat death. The universe expands forever. accelerating gradually. Galaxies separate. Stars burn out. New stars stop forming. Billions of years pass. Eventually, only black holes remain. Then, after Google years, 100 years, even black holes evaporate via Hawking radiation. The universe becomes cold, dark, empty. Just random photons traveling through ever-expanding space. Entropy maximized. No structures, no gradients, no possibility of complexity. Heat death. The most boring possible end, timeline with standard dark energy. About 100 billion years until galaxies outside the local group become unreachable. Accelerating expansion carries them beyond the cosmic horizon. We'll never see them again, never reach them. Our observable universe shrinks to just Milky Way and Andromeda, merged into Milkdromeda. Trillions of years until all stars burn out. The last red dwarfs finally exhausting fuel. The universe going dark, except for occasional white dwarf mergers, supernova flashes, rare events in endless darkness. Saturn 100 years until last black holes evaporate. Supermassive black holes at galaxy centers, slowly radiating away via Hawking radiation, finally disappearing, leaving nothing but photons and neutrinos and dark matter and whatever else is stable over those timescales. But if dark energy is stronger, if expansion is accelerating faster, the timeline compresses. Events happen sooner, and the end gets more violent. Dr. Robert Caldwell at Dartmouth proposed the Big Rip scenario, 2003, before the Hubble tension existed. But relevant now, if dark energy doesn't just cause acceleration but increases over time, if the energy density of space rises as the universe expands, then acceleration accelerates, gets faster, eventually overwhelming all forces, tearing apart bound structures. The Big Rip timeline depends on how fast dark energy increases. The equation of state parameter. W for cosmological constant, W Saturn 1 for dark energy that increases, W Saturn 1 phantom dark energy. The more negative W is, the faster the rip approaches. If W times 1.5, for example, Big Rip occurs in 22 billion years. Not trillions, not Google. 22 billion, less than twice the current age of the universe. What happens? Galaxy clusters tear apart first. Gravity binding them gets overwhelmed by accelerating expansion. Galaxies scatter, 60 million years before the rip. Then, galaxies themselves. Stars pull apart from galactic centers. Bound structures dissolve. 3 months before the rip. Then solar systems. Planets ripped from stars. Moons ripped from planets. Matter scattering. 30 minutes before the rip. Then stars and planets themselves. Matter tears apart. Molecular bonds break. Atomic bonds break. Everything disintegrating into fundamental particles. 30 attoseconds before the rip. Then space-time itself. The universe tears itself apart at quantum level. Everything ends, not with cold entropy, with violent destruction. If W is significantly less than 1, if dark energy is phantom, the Big Rip is inevitable, Caldwell explained. And the timeline depends sensitively on the exact value of W. Current measurements suggest W is close to 1, maybe 1.03 plus 0.05. That puts Big Rip trillions of years away. No concern, but if W is actually 1.2 or 1.3, if measurements are slightly wrong or if W is evolving, the rip could be much sooner. Billions, not trillions. The Hubble tension might indicate W evolution. Maybe dark energy was weaker in the past, or closer to 1, standard acceleration. But now it's getting stronger, decreasing, acceleration increasing. That would explain why CMB measures slower expansion and local measurements measure faster. The expansion rate is actually changing, increasing, getting faster as dark energy gets stronger. If that's true, the far future is different, more violent, sooner, And we don't know the timeline because we don't understand what's causing the acceleration to accelerate. November 2025. A workshop at Kavli Institute for Theoretical Physics, UC Santa Barbara, titled The Hubble Tension, Crisis in Cosmology. 50 leading cosmologists, observers, theorists, statisticians, all gathering to address the elephant in the room, the problem that won't go away, the crisis that's been building for a decade. Dr. Adam Rees presented the latest local measurements, Webb data, supernova data, Cepheid data, all converging on 73, all extremely precise, all contradicting Planck. The measurements are not going to change, Rees said bluntly. We're at the limit of systematic uncertainty. Error bars can't shrink much more. This is the answer. 73. The early universe data disagrees. That's not measurement error. That's physics. New physics, or wrong physics. Something fundamental is missing from our model. Dr. Lloyd Knox from UC Davis presented CMB analyses. Planck, ACT, SPT, all giving 67. All extremely precise. All robust to systematic checks. CMB measurements aren't budging either, Knox said. We've checked everything. Foregrounds, calibration, beam uncertainties, instrumental systematics. Nothing changes the answer significantly. It's 67. Early universe expands at 67. Current universe expands at 73. If both are true, something happened in between. Something changed the expansion. Dr. Eleonora Di Valentino from the University of Sheffield presented theoretical possibilities. We've explored dozens of models. Early dark energy, extra radiation, interacting dark sectors, modified gravity, decaying dark matter. Every idea that might explain the tension. Some help. None solve it completely. We're stuck, unable to find a theory that explains all observations while maintaining predictive power and physical motivation. She pulled up a plot, showing constraints from different observations. CMB, supernovae, baryon acoustic oscillations, weak lensing, large-scale structure. In standard cosmology, all these constraints intersect at one point. Consistent cosmological parameters. The model works, but when you allow for modifications, early dark energy, extra radiation, whatever, the constraints shift. Sometimes they overlap better, sometimes worse, but you never get clean intersection. Never get a model that explains everything beautifully. You trade one problem for another. The crisis is that standard cosmology works too well, Di Valentino said. Except for the Hubble tension. Lambda-CDM explains nucleosynthesis, CMB, structure formation, supernova cosmology, galaxy clustering, gravitational lensing, everything except the Hubble constant. Modifying the model to fix the Hubble constant risks breaking everything else. That's why we're stuck. We need new physics that solves the tension without creating new tensions elsewhere. Dr. George Evstathiou from Cambridge pushed back against panic. Maybe we're overreacting. Maybe there are subtle systematics we haven't found. Cepheid metallicity dependencies, supernova evolution, extinction corrections, something making local measurements systematically high, or CMB systematics we've missed. Foreground subtraction, lensing effects, something making early universe measurements systematically low. I know that's unpopular to say, Evstathiou continued. Everyone has checked everything. But the history of cosmology is full of systematic errors we didn't discover until later. We thought we'd measured the Hubble constant as 500 kilohertz MPC in the 1930s, then 100 in the 1980s, then 72 in the 2000s. Each time, we thought we were right. Each time we found hidden systematics. Maybe this is another case. Maybe in 10 years we'll laugh about how we thought there was a crisis. Dr. Wendy Friedman responded carefully. George, I respect that perspective. And yes, we should remain skeptical. But this feels different. Multiple independent methods give 72 to 73. Not just Cepheids. Not just supernovae. Gravitational lensing. TRGB. surface brightness fluctuations, maser distances. Every late universe measurement converges. That's not one systematic error. That's either conspiracy of systematics, unlikely, or real tension. And the CMB measurements are rock solid, she continued. Planck is the best space mission ever flown for this purpose. The error bars are tiny. The systematics are controlled. When George says we might find CMB systematics later, I ask, what systematics? What could possibly be wrong that would shift the answer by 9%? We've looked. We can't find it. At some point, we need to accept what the data tells us. Dr. Mark Kamienkowski from Johns Hopkins offered a middle ground. Maybe we're asking the wrong question. Instead of, which measurement is wrong? He or what new physics explains this? Maybe we should ask, what does the tension tell us about the universe? What is the universe trying to teach us? The tension says the early universe and late universe don't match. That implies evolution. Something changed. The universe today is not a simple extrapolation of the universe at recombination. Something happened in the 13.8 billion years between. Something we didn't include in Lambda-CDM. What is it? Maybe it's early dark energy. Maybe it's new particle physics. Maybe it's quantum gravity effects we haven't calculated. Maybe it's something we haven't even thought of yet. But the universe is sending a signal, screaming at us. Our model is incomplete, and instead of fighting about measurements or defending standard cosmology, we should listen, accept the signal, find what we're missing. Dr. Catherine Fries from University of Texas presented an unsettling possibility. What if the Hubble tension isn't solvable? What if it's a symptom of deeper crisis? What if our entire cosmological framework is wrong? We assume the Friedmann equations apply universally. We assume the universe is homogeneous and isotropic on large scales. We assume general relativity is correct. We assume the cosmological principle. But what if one of those assumptions is wrong? What if the universe is more complicated than Lambda-CDM can represent? What if we're not in a typical region? What if the Milky Way is in an underdense bubble? Local expansion rate would be different from global average. CMB measures global. Local measurements measure local. Different regions, different rates. No contradiction, just geometry. Or what if general relativity breaks down at cosmic scales? What if dark energy is a sign that Einstein's equations need modification? Not small tweaks, fundamental revisions. That would change everything. Decades of work, countless papers, all based on wrong foundations. That's terrifying. But possible. The room fell silent. This was the nightmare scenario. Not measurement error, that could be fixed. Not new physics, that could be discovered. But wrong foundations, wrong framework. Everything needing to be rebuilt from scratch. Careers' worth of work potentially invalidated. Textbooks rewritten. The entire structure of modern cosmology revealed as approximation that breaks down when tested precisely enough. I don't think we're there yet, Dr. Rees said finally. I think new physics is more likely than wrong foundations. But Catherine's point stands. We need to remain open to radical possibilities. The universe doesn't care about our comfort, doesn't care if the answer is convenient or inconvenient. It is what it is. And our job is to figure out what that is, even if it means abandoning cherished assumptions. The workshop concluded with no resolution, no consensus, no solution, just acknowledgement that the crisis was real. Growing, demanding attention, forcing cosmology to confront its greatest challenge in a generation. Despite the crisis, despite the confusion, work continues. Astronomers gathering more data, better data, testing theories, eliminating possibilities, narrowing the solution space, refusing to accept defeat. Dr. Rachel Beaton at Princeton leads the Carnegie-Chicago Hubble program's continuation. Using Webb, observing more Cepheids, more calibrators, building the most precise distance ladder ever constructed. Target, reduce error bars to plus 0,5 command SMPC. Make local measurements so precise that no systematic error could hide. If we can measure H0 to 0.5%, will either definitively contradict CMB or find the systematic we've been missing, Beaton explained. Right now there's wiggle room. Error bars of 1-2 kilitri quadrats MPC. Small enough to create tension but large enough to allow skepticism. Get to 0.5% and the skepticism disappears. Either we're right and CMB is wrong, or we're wrong and CMB is right. No more ambiguity. Her team has Webb time through 2027, observing 50 Cepheid hosts, measuring thousands of individual Cepheids, cross-checking photometry, comparing infrared to visible, eliminating extinction uncertainty, eliminating metallicity effects, making the cosmic distance ladder unassailable. Dr. Dan Skolnick is planning Pantheon++, the next-generation supernova survey, 3,000 supernovae, double the current sample, reaching higher redshifts, better calibration, better light curve sampling, better correction for dust and evolution effects. Supernovae are our best standard candles, Skolnick said. But we can do better, more data, better understanding of supernova physics, better corrections. We're getting to the point where supernova systematics will be smaller than statistical errors. Then we'll have the true expansion history of the universe, all the way from today back to redshift 2. That history encodes the physics, tells us what dark energy is doing, whether it's constant or evolving, whether the tension is real or measurement artifact. Launch target for the survey, 2026-2030, using ground-based telescopes. Rubin Observatory, next-generation extremely large telescopes, finding thousands of supernovae per year, the largest supernova cosmology dataset ever assembled. Dr. Colin Hill is pushing for CMB-HD, a proposed next-generation CMB mission, higher resolution than Planck, better polarization sensitivity, measuring CMB to fundamental cosmic variance limit, the ultimate CMB mission, after which no improvement is possible. You've measured everything measurable. CMB-HD will either solve the tension or prove new physics exists, Hill argued. If there are hidden systematics in Planck, CMB-HD will find them. If there aren't, CMB-HD will confirm Planck with even higher precision. Drive the error bars to 0. Make the 67 measurement absolutely definitive. Then there's no escape. The tension is real. New physics is required. We'll have to face it. The mission is in proposal stage, competing for NASA funding. Launch target mid-2030s, a decade away. But necessary. The definitive measurement that settles the early universe side of the tension forever. Dr. Licia Verde is developing better statistical frameworks. Multi-messenger cosmology, combining everything. CMB, supernovae, BAO, weak lensing, strong lensing time delays, tip of the red giant branch, surface brightness fluctuations, everything in one coherent framework, accounting for all correlations, all systematics, all uncertainties. The future isn't single measurements, Verde explained. It's synthesis, taking all data, all methods, combining them properly. Statistics tells us how to do this, how to weight different measurements, how to account for systematic uncertainties, how to find the best fit cosmological model given all observations. That's how we'll resolve the tension, not by better Cepheids or better CMB, by better combination of everything. Her framework is already influential. Multiple collaborations use her methods, and the conclusions are consistent. With current data, the tension is unresolvable. No combination of standard cosmology parameters explains all observations. Something is missing. Meanwhile, theorists explore increasingly exotic possibilities. Dr. Sunny Vagnozzi at Cambridge proposed cosmological wormholes, space-time connections between distant regions, affecting light propagation, changing apparent distances, creating illusory tension where none physically exists. Dr. David Spergel, former head of astrophysics at Simons Foundation, advocates for dark radiation, a new form of radiation energy. Not photons, not neutrinos, something else, contributing to cosmic energy density, affecting expansion, explaining tension without exotic physics. Dr. Lloyd Knox suggested cosmic topology might matter. Maybe the universe isn't simply connected. Maybe it wraps around itself. Finite volume. Weird geometry. That would affect CMB predictions. Change the derived Hubble constant. Resolve tension through geometry rather than new physics. Each proposal is carefully considered, calculated, tested against data. Most fail. They predict something else that contradicts observations. But occasionally one survives, barely consistent with everything, providing possible solution, adding to the list of viable alternatives. The scientific process continues. Data accumulating, theories proposed, tests conducted, failures acknowledged, successes tentatively celebrated. This is science working as it should, facing a problem, refusing to ignore it, systematically attacking it from every angle until the solution emerges. It's just taking longer than anyone expected, and the answer might be more radical than anyone hoped. December 2025, Dr. Adam Rees published a perspective article in Nature Astronomy. Title: Living with the Hubble Tension. The article acknowledged the crisis had no immediate solution, might not have a solution for years, maybe decades, and cosmology needed to accept that reality. Work with it. Move forward despite uncertainty. We're in a situation cosmologists haven't faced since the 1920s, Rees wrote. A fundamental contradiction in our observations. Two precise measurements of the same quantity giving incompatible results. In the 1920s, the solution was new physics, general relativity, expanding universe, revolutionary concepts that transformed our understanding. Today, we might need another revolution, another fundamental revision. But revolutions take time. Meanwhile, we can't stop doing cosmology, can't wait for the tension to resolve. We work with what we have, acknowledge the uncertainty, be honest about what we don't know, and keep measuring, keep theorizing, keep testing. Eventually, truth emerges. But sometimes it takes decades. The article resonated. Cosmologists shared it widely, because it articulated what many felt: frustration, confusion, but also acceptance. This is the state of the field. This is where we are. We don't understand the universe as well as we thought, and that's okay. That's science. If we understood everything, there'd be nothing left to discover. Dr. Priyamvada Natarajan at Yale wrote a companion piece, The Beauty of Uncertainty, arguing that the Hubble tension is actually exciting, a sign that cosmology isn't solved, that mysteries remain, that the universe still surprises us. Imagine if everything matched perfectly, Natarajan wrote. If every measurement agreed, if Lambda-CDM explained everything with no discrepancies, that would mean we're done. No more discoveries to make. Just refining decimal places. How boring. How disappointing. The Hubble tension tells us the opposite. We're not done. We're not even close. The universe has secrets we haven't uncovered. That's thrilling. That's why we became scientists. To discover. To learn. To be surprised? The tension is a gift. An opportunity. A promise that revolutionary discoveries lie ahead. Not everyone agreed. Dr. George F. Stathiou remained skeptical. I think we're being too dramatic. The tension might just be systematics. We've been wrong before, declared crises before, and resolved them with better measurements. I suspect this is the same. In 10 years, we'll look back and wonder why we were so concerned. But most cosmologists sided with Rees and Natarajan. The tension felt different, more robust, more persistent, more likely to represent real physics than measurement error. Public perception mirrored the scientific community. Science communicators explained the crisis, the implications, the possibilities, and public reaction was fascination. Not fear, not confusion, fascination. The universe doesn't make sense. Physics might be wrong. New discoveries coming. People loved it. YouTube videos about the Hubble tension got millions of views. Podcasts dedicated episodes to it. News articles explained it in accessible terms. The crisis became mainstream. The public engaged with cutting-edge cosmology, following the debate, understanding the stakes, rooting for resolution or revolution. Either way, excited to see what comes next. January 2026, a new player entered the game. China's Zhuntian Space Telescope, launched December 2025, co-orbital with their space station, 2-meter mirror, massive field of view, deep infrared capability. Purpose? Survey astronomy, mapping the sky, finding transients, measuring distances, and, relevant to Hubble tension, observing Cepheids and supernovae independently of Hubble and Webb. Dr. Lei Hu at the National Astronomical Observatories of China led the cosmology program. Zhuntian will provide independent calibration. Different telescope, different instruments, different systematics. If Western measurements have systematic errors, Zhuntian will find them. If Western measurements are correct, Zhuntian will confirm them. Either way, we contribute to resolving the tension. First results expected mid-2026. Cepheid observations in dozens of galaxies. Supernova follow-up. Distance measurements, everything needed for independent Hubble constant determination. The international effort expanding. More data, more perspectives, more chances to find the answer. The crisis had become the focal point of observational cosmology. More telescope time, more funding, more careers, more attention than any other topic. Because solving it meant understanding the universe. Failing to solve it meant living with profound uncertainty. Either outcome was significant, either outcome drove science forward. March 2026. Dr. Wendy Friedman gave the invited lecture at the Space Telescope Science Institute's Spring Symposium. Title: The Hubble Constant. A Century of Progress and One Persistent Problem. She traced the history. Hubble's original measurement, 500 kilometers SIMPC, wrong by factor of 7, due to confusion about Cepheid types, mixing populations, systematic error, Sandage and Tamman. 50 kilometers SMPC, wrong by factor of 1.5, due to Cepheid distance scale issues. More systematic error, her own work in 1990s, 2000s. 72 T kilometers SMPC, close, very close. Maybe right, or maybe slightly high due to subtle systematics we haven't found yet. Planck. 67 kilometers MPC, from completely different method, completely different physics, contradicting local measurements, creating the tension. We've been measuring the Hubble constant for 100 years, Friedman said. Every generation thought they had the answer. Every generation was wrong, or at least imprecise. Are we different? Are we finally right? Or will future astronomers look back at our 72 versus 67 debate and laugh at what we missed? I think we're right this time. I think both measurements are correct. And that means new physics. But I could be wrong. History suggests humility. The universe has fooled us before. It could fool us again. We need to remain open, skeptical of ourselves, willing to admit error if error exists. But we also need to take the data seriously. The measurements are precise. The systematics are controlled better than ever. If this isn't the answer, if there are still hidden errors, they're incredibly subtle. More subtle than anything we've encountered before. At some point, skepticism becomes denial. At some point, we have to accept what we're seeing. So where does that leave us? With a mystery, a profound mystery. The universe expanding at two different rates depending on how you measure it. Either our measurements are wrong in ways we can't detect, or our theories are wrong in ways we haven't realized, or something new exists that we haven't discovered. That's where we are. That's where we'll be for years, maybe decades, working, measuring, theorizing, testing, slowly narrowing possibilities, eliminating wrong answers, approaching truth asymptotically. This is science. This is how it works. Not breakthrough moments, not sudden revelation, just persistent effort, gradual progress, stubborn refusal to give up. The Hubble constant is 72 plus 2, or 67 plus 1, or something else entirely. We don't know. Not for certain, not yet. But we will, eventually, because the universe has an answer. It exists, out there, in the data, in the physics, in the observations we haven't made yet. We just have to find it, and we will, because that's what we do. We find answers, even when the universe makes it hard, even when the answers take decades, even when we have to revise our most cherished theories. We find the truth, eventually, always. That's the promise of science. That's why we do this. The audience applauded. Not because she'd solved anything, because she'd articulated what everyone felt. Uncertainty, determination, commitment. Faith not in current theories, but in the process, the method. The systematic pursuit of truth, regardless of how inconvenient that truth might be. April 2026. No resolution, no breakthrough, no sudden clarity, just continued work, continued measurements, continued debate, the Hubble tension persisting, the crisis deepening, the mystery enduring. Webb measured more Cepheids. Confirmed 73. Planck data reanalyzed. Confirmed 67. New supernova surveys launched. New theoretical proposals published. New tests designed. The scientific machine grinding forward. Slowly. Methodically. Inexorably. Because that's what science does. Faces the unknown. Confronts the inexplicable. Refuses to accept "we don't know" as final answer. "We don't know yet" is acceptable. "We'll never know" is not. The universe makes sense. Physics is consistent. Reality is comprehensible. If measurements contradict, one is wrong or both are right in a way we don't understand yet. Either way, the contradiction is temporary. Resolution is inevitable, even if it takes generations, and so the work continues. The measurements accumulate. The theories proliferate. The debates rage. And somewhere, in all that data, in all those equations, in all those observations, the answer waits. Patient. Certain. Real. The truth about why the universe expands too fast. Why space tears itself apart 9% faster than physics predicts. Why the cosmos refuses to obey the laws we thought governed it. The answer exists. We just haven't found it yet. But we will. Because the universe is expanding. Space is stretching. Galaxies are flying apart. And that expansion has a rate, a speed, a number. One number, one truth, one answer. We measure 73. We measure 67. Both can't be right in the way we think, but both are telling us something true, something important, something revolutionary. We just have to listen carefully enough to hear what the universe is saying. The crisis continues. The tension persists. The mystery endures. And cosmology, the science of the universe itself, faces its greatest challenge in a century. Either we're measuring wrong, thinking wrong, or the universe is stranger than we ever imagined. The answer, whatever it is, will change everything. Sleep well tonight. The universe is expanding around you, faster than Einstein predicted, faster than physics allows, carrying galaxies away, stretching space itself, and nobody knows why. When you wake tomorrow, the mystery will still exist. The tension will still persist, and scientists worldwide will still be working, still measuring, still calculating, still searching for the answer that explains why reality refuses to make sense. Sweet dreams, citizen of an accelerating cosmos. The universe is running away from itself, and we're trying to understand why. The answer might take decades, might require new physics, might revolutionize everything we know, but we'll find it. Eventually, because giving up isn't an option. The universe has secrets, and we're determined to uncover them all. If this journey through cosmology's greatest crisis made you realize how little we truly understand about the universe we inhabit, hit subscribe. Every week we explore cosmic mysteries that challenge the foundations of physics, from dark energy to quantum gravity to phenomena that break our best theories. The universe is stranger than we know, and we're still figuring it out. Don't miss the next mystery that breaks cosmology.